All right, so we're going to look at another example here. So in this particular case, I'm given the circuit here, and I want to follow my same 6-step process. In this case, I want to find the inductor current, which has been called I of t. Now in this particular problem, I want to, again, like any problem, somewhat be careful of the fact of how I define voltages and current polarities. In particular over here, right, I care about what's going to happen in this part of the circuit. So the switch is opening at t equal to 0, so I really care about this part of the circuit. So I'm going to make some definitions here using my passive sign convention. Right, so I've defined the current in this branch right here with the capacitor and the 3 ohm resistor as I sub c going this way, and I've defined I going this way in this branch through the inductor. So I'm going to just be careful to say that V3, the voltage across that 3 ohm resistor, is 3 times IC. Okay, and I'm going to be careful to define the voltage across the 6 ohm resistor as 6 times I. Okay, and V sub L is L di dt, and IC equals C dV dt. All right, I'm going to be careful to do that because if for some reason the current starts going in the opposite direction, the signs need to change here. All right, so we're going to use that later. All right, let's go through our multi-step process here. All right, what I really care about in this particular case is IL of 0 minus and VL of 0 plus, because I'm going to need those to be able to figure out my final solution for the inductor current. All right, so let's start. So step 1, and really step 1 has 2 subparts. So let's say part A is to get V sub C of 0 minus and I sub L of 0 minus. And in this case, they've been told to us as V of 0 minus and I of 0 minus. Okay? So to do this, we make the assumption that the switch has been, in this case, open for a long time before t equal to 0, so that everything's been able to get to steady state. So in other words, the capacitor voltage is not changing anymore. The inductor current is not changing anymore. So if I'm in steady state, our assumption is that our capacitors are open and our L's are shorts. Okay? And so we redraw the circuit in that condition before the switch moves. So I've got a 10 volt source, I've got a 4 ohm resistor. The switch is closed, remember, but in this case, the capacitor is an open, so I write that as V of 0 minus. Now the inductor is a short, so all I have over here is just simply a 6 ohm resistor, like that. Okay? Now, looking at this circuit, I can make some simplifications, right? How much current do I have in this branch right here where the capacitor is? Well, none. So this 3 ohm resistor doesn't matter at all, right? So effectively, I can even just sort of remove it from the circuit. It doesn't matter, right? Since there's no current flowing through it. It's still physically there, but there's no current there, so it doesn't matter in terms of my analysis. To figure out V of 0 minus, I can simply do a voltage divider here, and I can say V of 0 minus is equal to 10 volts times 6 over 6 plus 4. So you can see that that would be 6 volts. Okay. Now, if I wanted to get I of 0 minus, the inductor current is the current in that branch. I of 0 minus becomes, well, I know I have 6 volts across it from the previous part there. So 6 volts divided by 6 ohms is simply 1 amp. So, things to remember, V of 0 plus is the same as V of 0 minus. I of 0 plus is the same as I of 0 minus. So that's an important fact we're going to need later. IL of 0 minus equal IL of 0 plus is equal to 1 amp. Okay, all right. So we've got those important facts. Now the thing to remember is the capacitor voltage needs to be continuous from 0 minus to 0 plus. The inductor current needs to be the inductor current needs to be continuous from 0 minus to 0 plus. So that means the capacitor acts like a voltage source, and the inductor acts like a current source. Again, just for a short period of time, this is true. Okay, so now that helps me for my part B here, which is to get VL of 0 plus and IC of 0 plus. Okay, so for this we have to draw the circuit right after the switch opens. Okay, so let's do that. So right after the switch opens, all I have is these two branches over here. All right, so basically this branch with the 10 volt source completely gone. All right, so then basically what I can do is I can redraw the circuit. And when I redraw it, the capacitor in this case is a voltage source that is 6 volts, right, which is what I found for V0 minus. And I defined I sub C to be going that way. And then this guy here is our, what is he? He's a 3 ohm resistor. All right, so this was V3. And we said I is going that way. I've got my, what is that? That guy's a 6 ohm resistor. And I defined V6 to be going that way. Then the inductor is acting as a 1 amp source. I call this guy VL, and I've got that. Okay, that's my circuit. So in this particular case, all right, a couple of important things to note. The current in this circuit is 1 amp everywhere. All right, so I can see right off the bat that I sub C is actually -1 amp, because the current is 1 amp and it's going around in a clockwise direction. That means the current flowing in this part of the circuit where I've got the 6 ohms and the 6 volts and the 3 ohms is flowing against the IC arrow. So IC is -1 amp. All right, that's important for us to remember. So let's go through this. Let's do a KVL. So a KVL around this loop. Again, I look at the voltages and I'm going to go around in a clockwise direction. So I'm going to say 0 equals minus V3. Okay, so minus the plus on that resistor. And then I go minus the plus on the 6 volt source. So I say minus 6 volts. Then I go plus to minus on that resistor. So I say plus V6, and then I go plus to minus on the current source, so I write plus VL, and I've got that. Okay, so now what I need to do is to use my Ohm's law to replace V3 and V6. All right, let's do that. So V6 I'll do first. V6, I have a current flowing into the plus terminal, so I write that as 6I. Now in the case of my 3 ohms right here, I have my actual current is flowing into the minus terminal and out of the plus terminal. So that means that V3 is equal to minus I times 3 ohms. Okay? Because the current is flowing out of the plus terminal. So that means that 0 equals minus 3I. Right, minus from the KVL, and then a minus from the Ohm's law. So those guys are going to cancel each other. So minus 3I, minus 6, plus 6I, plus VL. Okay? All right, so in this case, I simplify everything. So I get minus 3 is 3. I is 1 amp. Minus 6 plus 6 times 1 amp plus VL. So I see that VL, and this is really at 0 plus. I just wanted to keep it simple. VL of 0 plus, these guys cancel, is minus 3 volts. Okay, so the voltage across the inductor right after the switch moves is minus 3 volts. Okay, all right, I'm going to need that later on. All right, I can also see, I guess, that I sub C of, if I care about it, 0 plus has to be equal to negative 1 amp. All right, that's not as important to me, but at least I know that. All right, so it's important to remember the fact that there's always two signs, right? There's a sign that goes with writing KVL, and there's a sign that goes with writing the Ohm's law. Okay. All right. So now we go to my step 2. So step 2 is to find DIL dt of 0 plus. That's always equal to the inductor voltage at 0 plus divided by L. That's our basic constitutive relationship for an inductor. So in this case, my L is what? It's 0.5 henries. So I have negative 3 divided by negative 1/2, or negative 6 amps per second. So in other words, the initial rate of change of the inductor current is 6 amps downward every second. All right, so that gets me to my step 3, which is to find my IL final. So what's my final inductor current? So again, that implies steady state, so long after the inductor current stopped changing, long after the capacitor voltages stopped changing. So the inductor is going to become a short, the capacitor is going to become an open. All right, let's draw that circuit. So remember, the circuit itself is this guy. And let's just get there's 3 ohm here, there's a 6 ohm here, and there's an inductor here. This is the circuit. So after switch moves, this is our circuit, right? If I look in steady state, the circuit becomes, here's an open, so here's V, and then there's R, and there's another R, and the inductor's a short. Well, without even doing any work in this case, I should be able to see, if I wait long enough and I get to steady state, this particular circuit has no sources. If there's no sources, it better be the case that there's no voltage or current left in the circuit, because there's loss mechanisms, this 3 ohm and the 6 ohm, the inductor and capacitor have to lose all of their energy, which means all the current and voltage better be gone. And in fact, that is what happens. If I look at this, V of V final is clearly going to be 0, and I final is also 0, right? There can't be any current in this circuit. If there's no current in this circuit, the inductor is a short. There's no current in this circuit. There's no voltage drop across the 6 ohm, no voltage drop across the 3 ohm, so the voltage on the capacitor is also 0. All right, so let's write up here the additional facts we know. So DIL of 0 plus is negative 6 amps per second. And we know that I final equals 0 amps. All right, so that information we're going to box. We're going to need it later. All right, so now, done a lot of good stuff. Now is usually the hard part. We need to do our step 3, which is to find our differential equation for IL. And again, in this case, we've called it I. So for I, which is the inductor current. Okay. So what that means is, in the way that we've said this, is I want to get an equation that looks like this, d squared I dt squared plus some constant times di by dt plus some constant times I equals some other constant. Okay, that other constant might be 0, might not be. All right, so that's the form we want to get, a differential equation that only has I in it. All right, so to do that, we're basically looking at this circuit right here. All right, so I'm going to write it like this. I'm going to say this guy is C. Here's 6 ohms. Here's my L. Here's my 3 ohms. And keep the same definitions we had all along. This is VL. This is V. This is IC. This is I over here. This is V6. This is V3. V3. All right, so to do this, let's do a KVL. All right, so I see with this guy, KVL, I get what? I get 0 equals minus V3. All right, so I go minus to plus. Again, I always go in this kind of clockwise direction. Minus V3 minus V plus V6 plus VL, like that. Okay, and now I want to get everything in terms of IL, right? So I know VL is L di dt. Okay, now V6 and V3. V6 is easy. V6 is 6I. All right. Now in this particular case, V3 was defined to be 3IC, but in looking at this circuit, IC equals minus I, so this guy becomes minus 3I. Remember, there's a current flowing into, but in this, so we defined it to be IC. So, and remember back in the very beginning, right? Very beginning, we said V3 equals 3IC. Well, because IC equals minus I, V3 equals 3IC, or minus 3I. So I plug that in here. I have 0 equals minus V3, or minus 3I, minus the capacitor voltage, like that. Okay? So I have 0 equals 3I plus 6I minus V plus L di dt. Okay? So that gives me 0 equals 9I minus V plus L di dt. Not quite there yet, right? In terms of, I wanted a differential equation in terms of only I, don't have that yet. All right, so I need to relate the capacitor voltage. Well, the capacitor voltage was, we know I equals, so IC equals C dV dt. But again, because IC is going the opposite direction of I, so it's because IC is equal to minus I can rewrite that guy like this. All right, and that tells me if I rearrange this guy, I do an integration, I get the integral of negative I over C dt is equal to V. Okay, so I can plug that in over here. So I get 0 equals 9I minus I over C dt plus L di dt. So the minuses go away and I get 0 equals 9I plus integral I over C dt plus L di dt. All right, we're almost done. All right, that's a differential equation, but we can't have that integral in there. So what we do is we take the derivative of both sides. So we take d by dt of 0, and give myself some more room here. So d by dt of 0, and that's equal to d by dt of this whole thing. So derivative of 0 is 0, obviously. This guy becomes 9 di dt plus, so the derivative of an integral is just, you get rid of both the derivative and the integral. They kill each other. So I get I over c plus L d squared I dt squared. So I have a differential equation now with a second order term, a first order term, and a zero order term. It's just not in my preferred form, right? I want to get a coefficient of 1 on the second order derivative. I don't have that. All right, so I rewrite this guy as 0 equals, so I divide everything through by L. All right, so I get, in this case, d squared I dt squared plus 9 over L di by dt plus I over LC. All right, now what is L and what is C? So in this particular case, C is equal to 0.02 farads and L is 0.5 henries. Okay, so L is 0.5 henries and C equals 0.02 farads. All right, so if I plug all that in, I get 0 equals d squared I dt squared plus 18 di dt plus 100 I, like that. Okay. All right, so with that, it's now time to solve. So I get to my step 5, which is to solve for I of t. As always, the solution is I final plus I transient. And we need to determine the form of that transient, whether it's an overdamped, underdamped, critically damped, whatever. All right, so that means, again, I need to write my differential equation, my homogeneous differential equation. In this case, it's the same. It's 0 equals that. That gives me my characteristic equation. So from this guy, I see my characteristic equation is s squared plus 18s plus 100 equals 0. All right, so to solve that, again, I always go to MATLAB. I say, all right, well, I pull off the coefficients of this guy. Highest order coefficient is a 1. Middle coefficient is 18. Zero order coefficient, the lowest one, always comes last. In this case, it's 100. I put them in those square brackets, and I say roots of that, all right, like that. And move this over here. And okay, I already have that here. So roots of 1, 18, 100. All right. Roots of 1, 18, 100. I take that guy and I evaluate it. And what do I get? All right. Ooh, I got complex roots. All right. Complex roots tell me that I'm underdamped. So let's see. I've got S1 equals -9. And I'm actually not going to say S1 and S2. I'm going to say S equals -9 plus minus J, the imaginary number, times 4.3589. Okay? So this guy tells me that I'm underdamped. So when I'm underdamped, this is the form of my solution, right? So we said S equals sigma plus minus j omega d. So I can see from this that the sigma is -9 and the omega d is 4.3589. All right, so using that, I can say, I can start plugging stuff in. So what was I final? Well, I wrote that down from before. I final was 0 amps. Okay. So I final was 0 amps. I transient is given here in the notes. So that's going to be equal to, in this case, e to the negative 9t times k1 cosine omega d. So omega d was 4.3589. So we say 4.3589t plus k2 sine 4.3589t, like so. Okay? All right, so this guy is a decaying sinusoidal thing. Okay? So let's look at step 6. Step 6 is a bit of a mess here. All right, step 6, I want to solve for my unknowns, K1 and K2, right? So with this, I want to go back to this guy that I saved up here, okay, and bring him down. Okay, so all this boxed information is helpful to me now. So my I of t was this. All right. Now the important thing is, in solving this guy, I've already kind of given you the results. I plugged in, well, if I plug in t equal to 0 into this expression here, the cosine term becomes 1 when I plug in cosine of 0. Sine of 0 becomes 0. So I can see from this that I of 0, which is 1 amp, has to be equal to I final, which is 0, plus K1. So I can see right now that K1 is equal to 1. I also have that di by dt is equal to minus 6. Again, taking the derivative of this expression here is nasty, but I've already taken the derivative of the general form and plugged in 0. So I can do that here. So dx0 by dt is equal to K1 times sigma plus K2 times omega d. And we already said our sigma was minus 9. So this is minus 9. And we know that K1 is 1 plus K2 times omega d. And omega d is 4.3589. So let's write this as 4.3589 K2. All right, so this is one equation and one unknown. I just need to solve. If I do that, K2 becomes equal to 0.6882. So that our final result, all right, essentially becomes I of t equal to e to the negative 9t times cosine 4.3589t plus 0.6882 sine 4.3589t. All right, that ultimately is our final answer. So what this says in physical terms is that we have a cosine and sine that are decaying at a rate of 4.3589. So this is, well, not decaying at that rate, but this is a cosine with that frequency in radians per second, and its amplitude is decreasing because of this exponential function that it's multiplied by. So that's what we get when we have an underdamped response.